Hierarchical Neural Dynamic Policies. Current robot learning methods take in an observation as input, process it via a black box neural network policy, and output a low-level action. We then take that action, get a reward, and update the policy. This kind of setup has been successful and applied to a lot of tasks, as you can see here. But they all have one commonality. They're quite quasi-static. The robot can take as much time as it wants for each time step. In contrast, humans move in much more dynamic ways. So how do we do this for robot control? Dynamical systems are omnipresent in nature and may help here. They provide an efficient way to encode continuous motions. They have in fact been used in previous robot learning approaches, for example, the seminal work of dynamic movement primitives, or DMPs. However, DMPs are limited in their ability as they require dense supervision and are unable to handle unstructured image data. Due to these limitations, we leverage our prior work, which embeds dynamical systems inside policy networks called neural dynamic policies, or NDPs. Given unstructured state input, an NDP outputs DMP parameters, which are then integrated to produce a trajectory. Here's an example of a 1D rollout of an NDP policy and a vanilla policy. The embedded structure in NDPs allows for smoother actions and for reasoning in the space of plausible trajectories. While NDPs produce good results in single goal settings, it is easy for single dynamical systems to overfit to trajectories. So can we build generalizable robot policies for dynamic tasks in the real world, only operating from raw images? This means that we must be able to handle diversity in the task without using any task-specific knowledge. We aim to do this by combining the ability of NDPs to reason in the space of trajectory distributions with the ability of modern deep robot learning methods to learn from unstructured image data. We break down the task into small regions and overfit local NDPs to ensure success. We then distill the local NDPs into a global NDP, which on the other hand is meant to operate on the entire space and only works from the image of the scene. We deploy the global NDP on the robot and use the collected trajectories to iteratively refine both local and global NDPs. Due to this local to global structure, we call our framework Hierarchical Neural Dynamic Policies, or HNDPs. To summarize, we first solve the dynamic task locally and then harness deep learning to fit a global NDP. We perform large-scale visual imitation learning experiments on the real robot. We evaluate on scooping. We provided very few demonstrations collected by hand. We show some sample results of trained HNDPs compared to guided policy search, or GPS, one of the baselines used in our paper. The robot is operating from images only, unseen at training time. We can see that not only HNDPs are able to perform the task smoothly, but they can also adapt to a change in bowl location. We also evaluate on pouring using a similar setup as scooping. Here's a comparison against GPS for pouring. As you can see, HNDPs are much better here as well. Finally, we evaluate HNDPs on a digit writing task. Here's a comparison against GPS for writing. The only input to the agent is an unseen image of a desired digit, which in this case is a 4. We can see that HNDPs produce a much more accurate and better looking 4. One of the main contributions of our work is thorough experimentation in the real world. We present test success rates for all 3 tasks. We thoroughly evaluate various components of the method. Our axes of evaluation include ablating local to global structure, the need for iterative refinement, as well as a comparison to traditional neural networks. We find that HNDPs strongly outperform baselines. The scooping and pouring tasks were quite challenging, and mostly our method was the only one that worked on them. We also apply HNDPs with reinforcement learning. We see that HNDPs outperform all prior methods in various dynamic tasks with high degree of stochasticity and diversity. Thanks for watching this talk. For more information, we encourage you to visit our poster and our website.